Good evening, everybody. 7:30, let's get started. So tonight we are actually starting on the real computer architecture. We're done with all the review of the previous course, topics from the previous course which are needed here. And now it's the real part of the architecture. So I hope things will get interesting to you from this point onward. So we started with this sequential ALU design, and then I suggest you to go to the other part, next module, and at least finish till the R type data path control path design. Hope you have done that before coming to the class. Any question from those two topics? Let me check the discussion as well. Module 4, module 5, there's nothing. Okay, so essentially what this sequential ALU part, by the way, just to note, this is just one of the possible design. It is not the design, not that every processor has a similar type of ALU, but it is one of the possible design that a sequential ALU can design with. Okay, so this is just an example that how do you go and design an ALU given all the different components that you have. More interesting part. I would like you to focus more on this processor design side and grasp the very top level conception. What is the major thing inside that process? So we all probably understand by now the processor designing has two distinct parts. One is the data path and another is the control path. So you can think of the data path as as a combination of different data crunching element. Just let's think in that way. Okay, something like this way, like your processor is it's a big, let's say, a block. Let me just. So one part is data path, and other part is control path. So what data path has? Data path may have several different data crunching elements. In the simple processor, like in this class, what we did, mostly the data manipulation is through the ALU. And there is register file as a storage, and there is a memory component and all this stuff. But in general, as a general concept, it can have many different components. And incoming data, let's say this is my incoming data. Those can be routed through various of these data crunching element, like split up, joining, etc. But end of the day, it gives out some outcome from it. So this is your data path, which manipulates the data through these different components inside these subpath. And your controller is basically the control path is mainly the controller which issues the signal to the various component in the data path. There is a commanding signal to various component of the data path, which controls the flow of the data through this data crunching element. Okay, so very top level view is like this. With respect to that, we just started to design our own processor at the component level, at the gate level. And there, what we have seen so far, how the instruction fetch data path works. Like it involves the program counter, it involves one adder inside it, and it basically uh, give the address of the next instruction to be fetched from the instruction memory. And then we moved on to the R-type instruction data path, where we introduced there are this register file, there is ALU. It doesn't have any memory component in it. It's basically register bound operation. And we have seen that main theme is that class by separate classes of the R-type function, like we have the logic class, we have the arithmetic class, we have special like the shift amount, for example, shift operation. We design the different data path using this ALU register file. And then at the end of the day, we superimpose this data path on top of each other and try to find out if there is a conflict between the incoming data onto a specific data crunching resource like ALU or register file. And if there is a conflict in the incoming data, we resolve that conflict by placing a multiplexer to select which data to pick up for that specific instruction. So that's the general theme. In the I-type instruction, we'll also see the similar approach. But in the sense, I-type instruction data path design is complex because almost each of the instruction is a different data path. We cannot just like the R type, we cannot just classify, okay, this is my arithmetic, it follows the similar data crunching route versus this is the immediate, this is the like logical operation, it follows the other route and so on and so forth. It is not simple like that. Almost each of the separate instruction has its separate data path. Only cluster is that arithmetic immediate operation and logical immediate operation. Other than we have load word, store word, which involves the memory, data memory, and also it has these jump and link. No, not jump and link is a J type. It has other one or two different. I forgot at this point, but we'll see. Like, but point is that with all this complexity, you need to use more multiplexer on the I-type data path. Okay, and then we'll design the J-type. And at the end of the day, we merge this R-type data path, I-type data path, J-type data path together on each other. And again, look at the different incoming data conflict, and start placing multiplexer on those to resolve those conflict points. So at the end, you'll see we actually end up using a bunch of multiplexer throughout the whole design process. And that's kind of a very backbone to the processor design. All right, so question. Okay, so if we don't have any question, then let me a little bit give you that conceptual idea on this project to final implementation that you are going to do is this. Like, remember, like we have this 5-stage risk execution example that was the beginning of the semester to see how really an instruction works in conjunction with the memory. A little program like this, high-level program like this, assembler level program like this, how it works. So our focus is this, mainly this controller simulation model writing. So it has two parts of it. One is the easier part, which is like state machine generation. This is one separate module, which is instantiated in the controller. What it does per clock cycle, it simply cycles through this state a state is defined as combination of bits, right? So we have like 5 state, so we need like 3 bit to represent them. And we see each clock, at each clock it will go from like let's say 000 to 001, then 001, then 010, then 011, and so on and so forth. So we assign some bit patterns to represent some of the state, one of the state. So at end of the day, these state machine will just cycle through simply these 5 cycle forever. Then in the controller, what you need to do per stages, per state of this state machine, you need to decide what control signals and what data signal you need to send out through all these ports. Like you have bunch of ports on the controller side. Some of them is linked to the memory. Some of them are linked to the register file. Some of them are linked to the ALU. And not in all stages you need to control all these elements. Like, so basically if you don't need to control them, just put them in a passive mode, and maybe you don't need to drive anything out them if it is a data or address bus, something like that. So pay attention to the control signal, and if it is not an active operation, just put it in a passive mode. Like for example, for a register file, you can just keep it as a read mode. That's okay. It is like nothing is being changed inside the register file. Similarly for the memory, read these two read-write signal, you can just take it, you can just put it as a read mode if you're not doing anything. That's fine. Then it becomes something like implementation would be something becoming like bunch of if then else statement. Like if my state is instruction fetch, then set these, that signals. Okay. And if my state is ID RF, then set the other signals to this. And by the way, within that decision block, you may need to make some decision based on the operation code. So here at this point, you will be parsing out the incoming machine code and determine what that instruction really is. Now, if it is an like R-type instruction or maybe specific R-type shift instruction, then you need to take some specific action based on that. So your implementation would become like, if depending on the state, if my state is this, if my instruction is this or instruction group is this, something like that, do this action. So it is just repetition of that type of coding. If my state is instruction fetch, do this. If my state is instruction decode and ID and RF, then you already parse it. Then if it is a register instruction, then R-type instruction, then access the register file with that corresponding operand register values from the machine code and read them, issue the read signal to the register file, etc. Then on the exe phase, if it is the exe phase, then if it is the R-type instruction, then depending on the instruction, you basically send the operation code into the ALU and set up the operand 1 and 2 accordingly what you are getting back from the register file, and so on and so forth. Similarly on the mem state, if it is a memory bound instruction, if it is not a memory bound instruction, don't do anything, just be idle, right? Put the memory control signal to read, register file signal to read. ALU don't care, it's a basically combinational element. You don't need to worry about that one. Then if it is a write back, then you need to see if it is a register bound operation, which register to write in, and accordingly you need to set up the write address, write data, and put the register file into that write mode. So that is the overall theme. And your code would look like, again, like a bunch of if then else statement. And each if then state else, the block would be what are the signals you are setting for that specific condition. All right, any question? So
No, sir,
anyone
thank you.
start? Yes, you're it.
Said no, sir. Thank you.
Oh. So I hope you guys have started on project 2. So any comment from anyone on this project? You started facing problems, facing issues?
It's just tedious.
Yeah, it is. And as I said, like writing the code may not take much time, but most of the time you'll be spending on the debugging, like why something is not working, why these given programs are not producing the correct result, and so on and so forth. So that part you need to be very careful, and that part would be really complex.
Hey, Professor, as far as helping someone else goes with the project, what are the limitations? You basically cannot give your code to someone, right? But if they have a problem with the code, can you take a look at it and maybe suggest them a couple of things?
Yeah, that's what I would like you guys to do in your study group. Within your study group, discuss the problem you're facing. Even you can just discuss the strategies, right? What to do, etc. Only thing prohibited is you share the code, do copy paste from each other. That's the only part.
Okay.
Okay. You can share your test code as well, like test program. I have given only like 2 program, right? One is Fibonacci generation program, and another is a reverse Fibonacci generation program. That won't exercise all the instructions. So you need to come up with your own program so that you make sure each of the instruction in the given instruction set is being exercised, and you are sure that your processor is executing them correct. Okay, so our testing would include many other programs. So that means just passing on those 2 cases may not be sufficient.
Okay.
Okay, so test program you can share with each other. Absolutely. But remember to put a reference, okay? Or at least mention that, okay, this has been done in a group, or who wrote this, something like that.
But as far as submission goes, you only want us to turn in the files you provided us, right? Not the tests.
Not the test, but
Okay.
I would expect some description in the testing section of the report.
Okay.
Okay. Then we can actually stop tonight early, so that you can go back and actually concentrate on the project 2 and study on this processor design. This has very intense concept, okay, and very important concept. Like once you grab this concept, rest of the computer mystery would be really easy to you to solve. Okay, so grab this concept very clearly.
So, hello, Professor Petra.
Yes.
So it says on the schedule that next week we will be having a quiz at the end of the week.
Yes.
I believe it's next week.
Quiz 2, yes.
So it may have said this in the schedule, except I think I think I wasn't looking at that part, but it was like, what will we be doing next week? And will next week be studying material for the next, will we keep going into more material that is not on the quiz next week?
So we have next day is also this I path, I type, J type, that is scheduled for the 16th of March. So by the 16th of March, you should be able to complete that whole lecture 11. Means complete the complete the processor design. Okay.
Okay.
Then it will be like midterm review. Midterm is coming up of March 23. Okay. So after that, we'll restart other modules like instruction set architecture. Then we go into the more advanced topic like performance measurement and how you can improve the performance of a processor through pipelining, parallelization, all this stuff. Right. So focus on this, finishing this lecture 11, and then midterm.
Thank you.
So quiz 2 will cover up to module 5.
Quiz 2 will cover up till this lecture 11. Yeah.
Okay.
Yes, let me just look at the schedule, how it looks like. Yeah, quiz 2 is lecture 6 to lecture 11. That's what the quiz 2 is.
Okay, thanks.
You're probably going to go over this, Professor, but is the midterm supposed to be, you know, just like the quizzes we've had before?
It's not entirely similar. So I believe I have scheduled one. Yeah, we can discuss definitely. And there will be a practice midterm quiz also available from March 16. Yeah, it will be available on March 16 towards night. From that day, it will be available and you can participate on that practice midterm quiz and see how that format would look like. And I will definitely distribute some more information maybe this weekend. Okay, Abhijati?
Yeah, got it.
Abhijat, not Jati. Abhijat. Okay.
Yeah, close enough. No one ever gets it right.
Okay. Then let's stop tonight early and you go back to your implementation on project 2. I really want you to pick up on this. That is the core concept of computer architecture. And it will help you in your software programming tuning. Like whenever you write a program, you can think, you can visualize like, okay, hey, what is my computer doing inside, right? That's the level of conception I want you guys to bring in within you, all right? Then good night, everybody, tonight, and see you next week.